Welcome to The Explainer. Today, we're diving straight into the high-stakes, high-pressure world of industrial flange faces. We're going to be looking at the silent mechanical heroes and, well, sometimes villains of process facilities, power plants, and subsea pipelines around the globe. Now, if you design, maintain, or operate any kind of fluid systems, you know that keeping the product actually inside the pipe is priority number one. But how exactly do we achieve that at a microgeometric level? It's literally the question that keeps piping engineers up at night. Picture this. You're on the final stage of commissioning a high-pressure steam line. Your bolts are torqued to the exact spec, the gasket is brand new, the hardware is absolutely top tier, yet the joint fails. Why does mechanical tightness sometimes fall short of preventing a disaster? So the crucial point here is that in 90% of cases, the true culprit isn't the bolting or the pipe material itself. It's an overlooked mismatch at the sealing surface. Just a single microscopic scratch crossing the serrations or using the wrong face geometry can turn what sounds like a slight hiss into a full-scale multi-million-dollar plant shutdown. Okay, before we start climbing the pressure ladder, let's make sure we're anchored on the basics. What exactly is a flange face? Basically, it's the specific surface area designed to interface with your sealing element, which is the gasket. Its entire mechanical job is to translate longitudinal bolt tension into a uniform circumferential compression. That's what creates a reversible, leak-proof seal capable of resisting both internal liquid pressure, or hydrostatic pressure, and external mechanical loads. Okay, let's dive into this. We're going to cover 5 key areas today. First, the anatomy of a seal. Second, flat faces and fragile systems. Third, the raised face, which is the industry standard. Fourth, RTJs for surviving extreme pressures. And finally, specialized faces for precision matches. Let's start with Section 1, the anatomy of a seal. You see, understanding why a joint fails means we've got to understand the baseline physics of a flanged connection first. The mechanical sequence of creating a perfect seal is like a delicate dance. You have to tighten bolts in a precise cross pattern, usually doing passes of 30, then 60, and finally 100% of your final torque. That tension translates to uniform compression across the face. The gasket then deforms, filling in the microscopic machining marks, those 125 to 250 micro-inch concentric or spiral serrations, and effectively blocking any leak paths. Proper torque sequencing matters just as much as the hardware, because if you warp the joint during bolt-up, honestly, no face type in the world will save you. Moving right along to Section 2, flat face, representing our fragile systems. So here we are at the lowest pressure rung on our severity scale. A flat face flange has its sealing surface on the exact same plane as the bolt circle. There's absolutely no raised section. You'll primarily find these used in low-pressure applications, like your standard Class 125 or 150 systems, municipal waterworks, and typical HVAC setups. And because the load is spread across the entire face, they require full-face soft elastomer gaskets. They're specifically designed to mate with more brittle equipment housings made of cast iron, fiberglass, or low-strength bronze. Now, pay attention here because this is absolutely crucial. This is the golden rule of piping. Never, under any circumstances, bolt a raised face flange to a flat face flange. If you try to mate a steel raised face to a cast iron flat face, that raised section acts just like a fulcrum. When you crank down on those bolts, the concentrated load will literally snap the brittle cast iron housing right in half. And trust me, nobody wants to be the one holding the wrench when that happens. Let's step it up. Section 3, raised face, the standard. Let's see how this builds as we enter the realm of the undeniable workhorse of the process industries. Now, what's really interesting here is how a tiny fraction of an inch completely rewrites the physics of the seal. For standard pressure ratings, like your Class 150 and 300 flanges, the face stands proud of the bolt circle by just 1/16 of an inch. But step up to higher pressure standards, Class 400 and beyond, and that protrusion bumps up to 1/4 inch. So why does that tiny bit of elevation even matter? Well, it essentially concentrates your total bolt load onto a much, much smaller gasket area. This massive increase in contact pressure wildly boosts the joint's overall pressure containment capability. It's exactly why the raised face is the default standard for petrochemical refineries and huge power generation plants, pairing perfectly with spiral wound and composite gaskets. Getting into some serious territory now. Section 4, RTJ, surviving extreme pressures. But what happens when the raised face just isn't enough? Well, think about the number 800. Once your system temperatures exceed 800 degrees Fahrenheit, or your pressures climb to class 600, 900, or well beyond into high-pressure API 6A territory, those standard faces begin to fail. At this extreme threshold, ring-type joints, or RTJs for short, become absolutely mandatory. An RTJ flange completely ditches the soft gasket altogether. Instead, it features a precision-machined annular groove that accepts a solid metallic ring, usually oval or octagonal in shape. When you torque the bolts, it creates this fascinating wedging action. The metal ring actually deforms right into the groove, creating a rugged metal-to-metal seal. But you want to know the most incredible part? It's completely self-sealing. The intense internal pressure of the system actually forces the ring tighter against the groove walls, which prevents catastrophic blowouts in incredibly hazardous environments, like offshore deep-sea drilling. And finally, Section 5, Specialized Faces for Precision Matches. Sometimes a flat or raised connection just won't cut it. Tongue and groove, as well as male and female faces, have to be used in matched pairs. They lock together exactly like puzzle pieces. A tongue and groove setup features a raised ring that drops right into a matching depression, which is absolutely perfect for lethal services like liquid ammonia, where you simply cannot risk a gasket blowout. Male and female faces work in a very similar way, but use a larger surface area lock, making them the standard for custom heat exchanger shells. Both of these designs are completely self-aligning and physically shield the gasket from corrosive external elements. And this brilliantly illustrates the whole spectrum. Think of it as your ultimate cheat sheet for mapping face geometry to industrial severity. We move from the flat face in municipal waterworks at the low end, stepping up to the raised face for standard petrochemical piping, then jumping up into the extreme severity of offshore oil and gas with RTJs, and capping it all off with the highly specialized tongue and groove configurations for intricate equipment like pumps and heat exchangers. So, what does this all mean for us? We've seen today how something as unbelievably small as a 1/16 of an inch change in elevation, or just a microscopic scratch in a steel groove, dictates whether a massive industrial plant runs smoothly or fails catastrophically. The right flange face has to match the service medium, the pressure, and the mating component perfectly. It forces us to ask, if this level of geometric detail dictates the survival of these massive, high-stakes systems, what seemingly minor, overlooked details might be silently threatening the integrity of your own designs? Thank you for joining me for this explainer. And remember, always keep questioning the details.